This experiment is vibration of a cantilever beam. It is the first half of your formal lab report that you will perform during this section of lab. The cantilever beam seen here, represented as a 4-foot long aluminum beam, is mounted at the midpoint of a pneumatic shaker. Prior to beginning this experiment, the natural frequencies corresponding to the first 3 modes of vibration will be calculated. During the experiment, the resonant frequencies will be recorded and compared to these natural frequencies. During the second and third modes of vibration, nodal points can be viewed along the cantilever beam. These nodal points will be measured and later used during your data reduction. As with all lab experiments, it's important to practice good lab safety. Specifically in this lab, we want to make sure that none of the equipment gets damaged. The power amplifier you see behind me has a series of lights on it. The power on light should be on during the entire experiment. The red lights, though, symbolize overcurrent. If these lights are to turn on at any point during the experiment, turn off the power amplifier and wait for the lights to go out. At this point, you can begin experimenting again. With your natural frequencies calculated, check them with the lab TA to make sure they're accurate before moving on. Our first step is powering on the power amplifier. To do this, you'll turn the black knob to standby first and then to full power on mode. Turning this black knob to standby, we can see that the power on light turns on and the fan in the power amplifier activates. Turning the power amplifier to operate, the beam will begin to shake gently on the pneumatic shaker upon which it's mounted. Next, the function generator needs to be turned on. This dial right here should be turned from power off to the numbers either 1 or 10. These numbers represent a multiplicative factor that will get multiplied by our frequency dial seen here, resulting in our total frequency. I'll use the second mode of vibration as a demonstration. Turning from power off to 10, we can see that 0.6 is represented as the frequency here, and our multiplication factor of 10 giving us a total frequency of 6 Hertz. Because I know that the second mode of vibration happens around 18 Hertz, I'm going to begin tuning this into the dial. Turning this dial to 1.8 with our multiplication factor of 10 results in that natural frequency of 18 Hertz. The reason I'm choosing to dial in this natural frequency is because this frequency represents our ballpark estimate of where our resonant frequency for the second mode will occur. Telltale signs that our resonant frequency has been reached include a maximum deflection of the beam itself, as well as, for the second mode at least, one nodal point being seen. I'll begin now fine-tuning around 18 Hertz to find our resonant frequency. Watching the beam itself, I'm looking for, again, a maximum deflection, as well as a nodal point. Once I'm satisfied that I've reached my resonant frequency, I'm going to go ahead and record the reading on the function generator, as well as use the ruler to measure the distance from the center point of the beam to the nodal point itself. And this will be recorded and used later. Now, you also have to complete the first and third modes of vibration, repeating the same process. A stroboscope will be used later to get a more specific resonant frequency, as this is only good to 0.5 Hertz. Now that we've reached our resonant frequency, we want to get a more accurate measurement of the frequency. As I mentioned earlier, the function generator is only accurate to 0.5 Hertz. Currently, we have tuned in a 16 Hertz measurement. The stroboscope is in RPMs, so we need to convert Hertz to RPMs. Using a factor of 60, our 16 Hertz measurement becomes 960 RPMs. We'll use the coarse and fine-tuned adjustments on the stroboscope to dial that frequency in. When we shine the stroboscope at the beam, we'll know that we have reached our proper resonant frequency when the beam stands still. With the stroboscope tuned to 960 RPMs, we can see that the beam is still slightly moving. This makes sense because 960 is based off our initial estimate of 16 Hertz. Using the coarse and fine-tuned adjustments, we can make the beam stand still. With the beam standing still, we know that we have reached our appropriate frequency that represents the resonant frequency in our second mode of vibration. This experiment is resonant response of a cantilever wing. It is the second half of your formal lab report. This lab is similar to vibration of a cantilever beam, but in place of the beam, we have a transport wing mounted on an electromagnetic shaker. The first four natural frequencies corresponding to the first four modes have been previously calculated and can be found in your lab manual. The main difference between the transport wing and the cantilever beam is the nodal points. On the beam, nodal points were represented as single points, whereas on the transport wing, different patterns will develop for the different modes of vibration. These will later be analyzed and modeled in Pro-E. Now you're ready to begin vibration of a cantilever wing. Your lab TA should power on all of the equipment for you, so you do not need to worry about that. First, you need to take the measurements as well as angles of this wing, because you will later model it in Pro-E for a modal analysis. Next, you need to pour sand over the entire top surface of the wing. Be sure not to bunch the sand up in any one location. The sand will be used to visualize the nodal patterns that will develop for the different modes of vibration we'll be testing. For the purpose of this demonstration, I'm going to choose the second mode to model. We will tune in the frequency of 34 Hz into the function generator, much like we did on the cantilever beam. Using the coarse adjustment knob, we'll reach 34 Hz, and then use the fine-tune adjustment knob to reach the resonant frequency. Telltale signs that we've reached the resonant frequency include maximum deflection of the wing tip, as well as the formation of the nodal point, much like the cantilever beam experiment. When the sand begins to move, you know you're in the right path. As you can see, a nodal point has formed along this line. I'm satisfied that the tip of the wing has reached a maximum deflection, as well as the proper nodal point has formed, and I can now move on to modeling the other modes of vibration that we will be testing. A stroboscope can also be used to get a more exact measurement of the resonant frequency.